Use Moivre's theorem to prove this identity. So Moivre's theorem says that if we have cos theta plus I sine theta, and we raise it to the power of n, then this is the same as cos n theta plus I sine n theta. And you can prove that using Euler's relation. We're just going to use it here. So we want sine 7 theta here. And therefore, what I'm going to do is take this, the right-hand side, and let n equal 7. And then that is going to equal the imaginary part of the left-hand side. Because if you look at the right-hand side, we've got a real part, we've got an imaginary part. It must be that sine n theta is equal to the imaginary part of cos theta plus I sine theta to the 7. And here it goes. We've got a binomial expansion involving cos and I sine theta. Let's go for it. So we're going to get the imaginary part. Right, from now on, I'm going to be writing c instead of cos theta and s instead of sine theta, just to speed things up a little bit. So c to the 7 plus 7c1, c to the 6 times is, that's my I sine theta. By the way, that is equal to 7, plus 7c2, c to the 5, is all squared, and that is equal to 21, this term here. And we just keep going. This here is then 35. Again, 35. Made a mistake there, so that should have been a 4. And this is a 5. Remember, the power is always up to 7, so you can spot if you've made a mistake. That goes back to 21. That is 7. And then finally, it's just is to the power of 7. Okay, now we can take some shortcuts here, because we can just ignore that, because that is entirely real. And this term will be entirely real as well, because it's got I squared in there. And basically, it's every other term we can just eliminate straight away. So what are we left with? We've got 7 c to the 6 is, and then it's going to end up being, like when you do I cubed, you actually get minus I. So it'll be minus 35 c to the 4 is cubed. And I to the 5 takes us back to I. So it's plus 21 c squared is to the 5. Then I to the 7 is back to being minus I, to be minus is to the 7. Okay, so now I'm just going to write one more line. I can just basically remove the i's. We're going to get 7 c to the 6 s minus 35 c to the 4 s cubed plus 21 c squared s to the 5 minus s to the 7. Okay, that is what sine 7 theta is. I mean, this is an epic question, has got to be said. We want to get it all in terms of sine, remember. So we've got to sort out the causes. Well, let's do a little bit of groundwork down below. So cos squared is actually 1 minus sine squared. So what I can do is just replace that by 1 minus s squared in a bracket. Cos to the 4 is then going to be that squared, which will be 1 minus 2s squared plus s to the 4. And yeah, we can replace this. got to do this really carefully. But of course, the great thing is that, remember, we have the answer. So if you do make a mistake, you can hopefully figure out where it is. And then c to the 6 is going to be 1 minus s squared to the 3. And I'm just going to use Pascal's triangle to do this binomial expansion, which is another one. So we're going to get 1, then it will be minus 3s squared plus 3s to the 4 minus s to the 6. Okay. Before I multiply it all out, I'm just going to write it out once more, just to be on the safe side, have it next to each other. So 7s, I'm going to put the s to the left, 1 minus 3s squared plus 3s to the 4 minus s to the 6, then minus 35s to the 3, 1 minus 2s squared plus s to the 4 plus 21, 1 minus s squared. Oh, I missed out the s to the 5. Minus s to the 7. Okay, so that gives me 7s minus 21s to the 3 plus 21s to the 5. Some of these s's look a lot like 5s. You have to be careful here. Minus 7s to the 7. Then minus 35s to the 3 plus 70s to the 5 minus 35s to the 7 plus 21s to the 5 minus 21s to the 7 minus s to the 7. Okay, we've just got a single s term. So I've got my 7 sine theta. Then I've got minus 21s to the 3. I think I've made, oh yeah, that was a 5 there. Minus 35s to the 3. That is going to give me minus 56s to the 3, or sine cube theta. Then we've got 21 plus 70 plus another 21. Well, that's 42 plus 70. That is 112. And then finally, minus 7 minus 35 is minus 42. Minus 21 is minus 63. Minus s to the 7 is minus 64. So I think we can go straight there and write this down. Okay, it's pretty involved, but we've derived it, an identity for sine 7 theta. Okay, on to the next part. Now remember, if you got stuck, don't spend a long time like trying to find out what your mistake is for the sake of 1 mark. Okay, there's so many more marks in the paper. This is question 4. You do not want to run out of time on question 7 and the like. So, okay, if you're not quite there, just go with it. Just say, all right, I'll come back to it if I have got time. Now we can use this result. It says, hence, find the distinct roots of this equation. Wow, we're being asked to solve I can't remember what the name of this is, but it's to the power of 7. Septic, maybe? I'm not sure. So we got something, we can let x equal sine theta. And then this is going to become, well, that there is precisely this. So it's going to be 1 plus sine 7 theta equal to 0. See, that 1 is not part of the expression. We've got to have that there by itself. And then sine 7 theta is going to equal minus 1. We're ready to solve and do inverse sine on minus 1. Here's our sine curve. So it's actually going to be at 270 when sine is minus 1. So 7 theta is going to be 270. And we can just keep adding 360 on. 630, 990, and then 1350, 1710. That's enough to get us going. So then theta, we're going to divide each through by 7. That one happens to be 90, but don't worry about it. Just go with it. Okay, I'm going to include 2 more. Because when I find the next one, if I was to add 360 on again, then I've actually gone up 7 lots of 360. And so here to the next one would be adding on 360, and I definitely get the same value. So I only need to write 7 down. In the solutions, they just write down the first 2 positives and the first 2 negatives, and that is it. And they get 4 distinct answers. But I don't know how they know that there's going to be 4 distinct answers without kind of checking all of them. So if anyone can explain that to me, let me know. Just I don't get it. But now to find x, I'm going to find sine of each of these. Okay, and some of them are going to end up being repeated. But I only need to check these 7, and then any onwards would be repeats for sure. So first one, 0.623. Just going to round straight away to 3 decimal places. Next one gives us 1. Next one gives the same answer, 0.623. So I'm just going to reject that one. That means it's a repeated root. Next one gives minus 0.223. Then we get minus 0.901. The next one is the same, so just going to ignore it. And then we get another minus 0.223, so we're going to ignore that. And therefore, these are answers to 3 decimal places. You've got to include all of them. My recommendation is, yeah, just do exactly what I did. Just cycle through until you know you've done enough. We know at most there's going to be 7 solutions, but actually the point was that once I've added on 360 to this one, I'm definitely going to be cycling through the same set of solutions again because sine is periodic about 360. Oh, good question. Well done.